Okay, so now we understand a little bit about what Bn of k stands for, right? And now we're extending the example of always looking at a pair of points that were shattered given a set of endpoints. Now we're moving ahead and saying that, okay, k can take any value, right? And we looked at that example in the previous video, so let's move on and take it further. The question here that we're trying to answer is how many dichotomies can you list on 4 points so that no subset of 3 is shattered? And again, what I did here is just simply listed all those dichotomies such that no 3 were shattered out of the 2 to the 4 possible dichotomies. Okay, so these here for this particular situation, and you know how to write it, right? B43 is actually 11. So I could come up with like 11 possibilities. This is all the list of those dichotomies where none of the 3 points were shattered. Okay, now suppose we are given this list. What we are going to do now, and beginning from here, is that we are going to reorganize this. And how are we going to reorganize this? And again, like no need to get overwhelmed. We still will have like these 11 possibilities. I'm simply going to rearrange them, put things up and down a little bit. Let's look at how they appear once I have some kind of reorganization done. And moving on here, the basis of the reorganization essentially is going to be some prefixes, right? So let's look at these prefixes. What do you mean by prefix? Basically what I'm doing is I'm dividing or just like segregating the first 3 points here from the 4th one, and I'm calling this a prefix. So the set of first 3 points is a prefix, right? And some of these, if you look at them closely, appear multiple times. So this one, negative, 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 and negative, 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 is it's like repeated, right? And then if we look at like some of them, again, this one is repeated, the one in red, right? This is negative, positive, negative, negative, positive, negative, right? This is what the prefixes are repeated. Some of them are unique, right? For example, this blue one here, you don't see a positive, positive, negative anywhere in the entire list of dichotomies, right? So these are there only once. And even this one, right? This one is once. And what's going on here? This one also is once. Yeah, so basically we can come up with the ones that appear once and the one that appear twice, and this is going to be the basis for how we are going to segregate the dichotomies essentially, right? So this is what we are going to do going forward based on prefixes. We will segregate, as you will see, the dichotomies. Okay, great. How is that going to happen? Let's go here. So this is how we just segregated them. And again, even before moving here, let me just like show you what's going on, right? We looked at like this one and this one, like all negatives and all negatives. And although the prefixes were exactly the same, you can see that the x4, which maybe you can call a suffix, or the point that was left out, as like one of them as negative and one of them as positive. Why? Because like just remember that this is, to start with, this is what it was. It was B43, right? So no 3 points were shattered, and so this will have like an opposite suffix, which is x4 in this case, right? So we will have like these positives and negatives with a given prefix that's the same, right? So what we're going to do is, based on how these prefixes and suffixes are like appear in this entire list of dichotomies, we're going to segregate them. So basically, we are calling all those dichotomies whose prefixes appeared once only, for example, this one and this one and this one, as alpha. So that is these are going to be my alpha once only, and then the rest are going to be my betas. But the way my betas will be sort of distributed is going to be dependent on the value of my suffix, because you can say that there will be 2 betas. The first one is going to be like, for example, negative, negative, negative with the suffix value as negative. And then there is going to be another beta that is again going to have like the negative, 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 but the the suffix was this positive here. Yes, this is how I'll have like two betas, although they have like the same prefix, but the x4 value is different, right? So that's how we have segregated this B43 dichotomies as something like this. Let's again like analyze. Alpha, as I said, is prefix appears once only. So they're like, we are pretty clear on that one, right? We're pretty clear that this like appears only once. And so these are the dichotomies. These are three of them. So alpha is 3 in this case, right? And betas are 4 and 4, right? So this makes it 11, of course, right? The only basis for having two betas is essentially saying that the x4 or the suffix here is a negative for all of them. So maybe like at some point I'll be calling this as a beta negative and a beta positive. Essentially they are the same prefix, but the suffix or the x4 value is different. And of course, right, it will be different because that's what like that's why we had like B4 of 3, right? We cannot shatter all points. So this is how the segregation has been done. And because we started with this value B43, which was 11, and now we can safely say actually that B43 equals alpha plus 2 beta, right? Because here alpha plus beta is what essentially is, and this is 11, right? So we can definitely say for this situation at least that B4 of 3 is this alpha, which we define as prefix appears once, plus 2 times beta, which we define as prefix appears twice, right? So this is my basic definition. Using this, let's move further and let's focus on only alpha and let's say beta negative, right? This is what we called it. So let's focus on these two. Now here alpha plus beta negative is a list of dichotomy, like if you can see, on 3 points. And let's say I'm not focusing on x4 at all, right? So I'm only focused on x1, x2, x3, right? And this is a list of dichotomies on 3 points. And in this set of 3 points, there cannot be any subset of size 3 that's shattered, right? Because if that was the case, then the original set of 4 points, remember the B43, will also have that subset of 3 shattered, right? Which we know is not the case. We already know that we started with this like B43, where no subset of size 3 was shattered. That's what we began with, right? So we can safely say for only this part, although we are like only focusing on those 3 points, that there isn't that subset, right? So basically what we're trying to say that is this list of dichotomies at most of size B3 of 3 would be kind of constrained by this alpha and beta negative, or rather the opposite way, right? So beta, so basically let me write it down instead of like speaking, because then that doesn't make a lot of sense. And I'm just like putting this negative sign for us. Actually, it's the beta and the beta are the same, but just like so that we know that we are focusing on this part, right? And this at most can be not greater than B3 and 3. Why? Because that's what we started with, right? So if we are focusing only on 3 points, so my new n is essentially 3 and my k stays what it was, I can guarantee that in this like set of 3 points, any subset of size 3 cannot be shattered, right? It won't be shattered because we started with that. Okay, so basically what we are saying is we have this right now. We have this equation and let's keep it as it is, right? And then move on. Let's see what the other beta positive has for us. Okay, and just remember this equation, remember this relationship. Okay, so as I said, let's focus only on beta positive right now, right? Now, what we are going to do here is you can see that we are focusing on like these 3 points, correct? And we are going to imagine, or we are going to suppose, let me write it down. Suppose that a pair of points is shattered. Suppose a pair, in this particular case, although it's not shattered, but I'm saying suppose a pair is shattered. For example, let's assume x1 and x2 are shattered, right? Then in this beta positive, we will have all 4 pairs in which both beta positive and beta negative like we'll have 4 pairs in both beta positive and beta negative, and then like in beta positive we'll have all pairs with positives, and in beta negative we'll have all pairs with negatives, right? So that means in this entire set of dichotomies, like the full B4 3, sorry, B comma 3, yeah, the entire list, we will have those 3 points shattered, which is not the case. Let's say x4 combined. That's not possible because we started with b4 3, right? So that is impossible, which means that my b negative will not, my b positive will not shatter any 2 points, or my beta positive rather, not b. I'm like confusing. So that means, again, let me actually show you what I meant, right? So let's say in my x1 and x2, we're supposing that a pair is shattered, although as you can see x1 and x2 is missing this positive and positive, right? So nothing is shattered actually. We are just supposing that everything is shattered. And if that was the case, what I'm trying to show you, if that was the case, then these are the same points as this, right? This and this are the same points if we are only looking at x1 and x2. So basically I would have like all possibilities of x1 and x2 because I'm supposing that it has shattered everything, right? So all possibilities, this is what all possibilities is, and we'll have all possibilities here and again here, right? And also don't forget x4. Now x4 would have like these guys here, and x4 would have like these guys here, right? Because I'm taking care of like my beta negative and my beta positive, and I'm saying, let's say they were shattered. Now if I'll have like the same guys repeated here, this is going to shatter 3 points. Sorry, yeah, shatter a set of 3 points, which is x1, x2, and x4, which is impossible. Why? Because I started with b4 3. I already said that none of the 3 sets of points is shattered, right? So this is impossible. So this is kind of telling us that in our case, this beta positive, right, is sort of bounded by b of 3, 2, right? This means like my beta positive will not shatter any 2 points, because when we did that, when we said that suppose it will, right, it just showed us that this was impossible, right? So this is going to be less than that. Well, that's great. Now we have 2 results, one for alpha plus beta negative and a one for beta positive. And by the way, this beta negative and positive are essentially the same thing. They are betas, right? So going back to our original definition of beta, we can say that for this example, right? Therefore, for this example, because we earlier said that this example was equal to alpha plus 2 beta, which in turn is equal to alpha plus beta, right? And this particular part we've just proved, let me remind you here, is B3 of 3, correct? So I'm going to replace less than equal to B3 of 3 because we just proved that combinatorially that this is the case. And for beta positive, or just another beta, we also proved this, right? That this is this here, right? So I can also put that here, which is B, this value, 3, 2. We can actually go on with other values of B4 and 3 and prove, but I'm not doing that right now because this is enough to kind of generalize this argument and say that Bn of k is actually always less than equal to, I'm going to like replace these quantities with n's and k's, right? So we can actually generalize this and say this Bnk is less than equal to Bn minus 1. You can see because n, if this is n, so that we minimize confusion, and this is k, right? So this is n minus 1 and this is k as it is, plus b again n minus 1 and k minus 1. Okay, so this is what we are trying to derive, and we will see how this is super useful to us. So we have illustrated sort of this recursion problem, right? How to define this maximum number of dichotomies of endpoints such that no k are shattered is bounded by this sum, this recursive way of kind of generalizing it. And we have found essentially an upper bound, right? So what I'll do is because we have derived this generic form, and of course you can go and verify it for other values of n and k, just like we did it for 4 and 3 and sort of generalized it for any n and k. And then what we'll do is, going further in the next video, what I'm going to show you is how this is going to help us bound the growth function, because that's the essential question that we are trying to answer, right? So that's what I'm going to do now. Let's see you in the next video.